Hello, and welcome to Summarize Science, where we break down the latest research. Today, we're diving into the nurseries of new stars to solve a chemical mystery that has puzzled astronomers. This story is about methanol, a simple organic molecule, but with a special twist that helps us understand the birth of stars and planets. Methanol is found all over space, but scientists are especially interested in its heavy versions. This is where a regular hydrogen atom is replaced by deuterium, which is essentially a hydrogen atom with an extra neutron, making it heavier. There are two main places this can happen on the molecule, creating either CH2DOH or CH3OD. Based on simple statistics, you would expect to find 3 times more CH2DOH than CH3OD. But when astronomers looked at young stars, they found something weird. Around small, sun-like protostars, the ratio was often much higher than 3:1, sometimes even exceeding 10:1. And around massive protostars, the ratio was flipped, dropping to 1:1 or even lower. This discrepancy was a big question mark. Did this ratio get set before the star was born, or was it altered by the process of star formation itself? Answering this was impossible because no one had ever measured the ratio in a prestellar core, a cloud of gas that hasn't yet collapsed to form a star. That's where this new research comes in. Using the powerful IRAM 30-meter telescope, astronomers pointed it at 2 prestellar cores named L1448 and B213C6. And for the first time ever, they successfully detected the faint signal of CH3OD in L1448 and found hints of it in the other core. This is the crucial missing piece of the puzzle. With this detection, they could finally calculate the ratio of these two heavy methanol types at the very earliest stage of star formation. They found the ratio in the prestellar core L1448 is between 2.8 and 8.5. This range is right in line with the elevated ratios seen around young, low-mass stars. So let's recap what this groundbreaking discovery means. First, it provides strong evidence that the chemical signatures of these important molecules are established extremely early, in the cold, dark environment before a star even ignites. This means that young stars and their surrounding planet-forming disks inherit their chemistry, rather than creating it from scratch during their chaotic formation. This helps scientists better model the chemical starting conditions that eventually lead to planets, moons, and perhaps even life. This initial finding from 1 or 2 cores is a huge step forward. Future research will need to expand the search to more prestellar cores to see if this pattern holds true across the galaxy, further cementing our understanding of how star systems get their chemical beginnings. Thanks for joining us at Summarize Science.